Okay, hello class. We're going to continue on with chapter 10 here, and we're going to do some of these homework problems. And first things first, for problem 1 in part A, I'm going to leave this one up to you because this is a conceptual question. And so you just have to compare the two moments of inertia of the two objects. So go ahead and look up what the moment of inertia is of a solid cylinder and a hollow cylinder and then compare them. And just remember that the higher the moment of inertia, the harder it is to move that object, or the more likely it's going to resist a rotation. So going ahead next, we have how fast in meters per second is object A moving at the end of the ramp if its mass is a certain number, its radius is a certain number, and the height beginning is a certain number. So we're going to go ahead and we have H, we have M as quantities. They use capital M here, so I'll use capital M. And we have R. And so we treat this like a conservation of energy problem. And so what we're doing here is we're assuming that it's starting from rest, so there's no kinetic energy. And when it gets to the bottom of the ramp, it's going to have no potential energy. And so it only starts with potential energy, and then it ends with only kinetic energy. So what we can do here is we can say that through conservation of energy, we can say that mgh is going to be equal to the kinetic energy plus the rotational energy. So we have 1/2 I omega squared plus 1/2 mv squared. This is VCM technically, just to make sure that we are accounting for this, or we could just say VA because this is object A that we're talking about here. And so we go ahead and we're going to look up what I is for object A, and this is going to be I is equal to mr squared over 2. And so what we can do here is we can go ahead and say that this is the same m here. These are all the same m's. We don't have to worry about that. So mgh is now equal to 1/4 mr squared omega squared. And here we can say that that in this case we can go ahead and substitute in VA here, because that's what we're looking for, the translational velocity here. So we can go ahead and make sure that this is what we're looking for, plus 1/2 MA or MVA squared. Okay, so let's go ahead and substitute in VA here. So this is going to be 1/4 MVA squared plus 1/2 MVA squared, and so this is going to give us 3/4 MVA squared, and this is going to equal MGH. And so I believe that we're looking for V. So then we'll get rid of the M's, that's gone. And then we'll multiply both sides by 4 and then divide by 3 to, get our, and then take the square root and we'll get our final answer here. So then we'll see that VA is going to be equal to the square root of 4GH over 3. So then you plug in your numbers and you'll return your answer here. So then what we're going to do here now is, for the next part of the problem, is we're going to substitute in B's. We're doing this for object B now. And so we're going to get a different answer because we have a different moment of inertia. So in this case, we're going to go ahead and we're going to substitute in now what I is, and I is just that. So then we can go ahead and adjust this. This is going to be 1/2 now. And so then this is 1/2. And so then this is going to be just 1. So we can get rid of this. And that should be your answer. Yep. And then there you go. That's the velocity for B. Okay, so moving on. Next problem. Okay, so a solid sphere of mass m and radius r rolls without slipping down a rough incline that makes an angle theta with the horizontal. So what we're going to do is find the magnitude of the linear acceleration a of the sphere. Okay, so what we're going to have to do is we're going to have to talk about rolling friction and apply Newton's laws here. So remember that the sum of forces in a single direction, or x, are going to be equal to max. And so then here we can just start summing our forces. And then we're going to get mg sine theta from just what's the weight pulling the object down the ramp minus fs. And so what we can do now is we can say that the sphere rolls clockwise down the incline, so the torque due to static friction forces outward toward the viewer and negative. And remember that, so then we can say that t is going to be equal to negative fs r. So this is static friction here, and this is going to be equal to I alpha. And real quick, we can say for a solid sphere that I is going to be equal to 2/5 mr squared. And so then solving for static friction here, we get that Fs is going to be equal to I alpha over r, and this is going to be negative as well. And so from here, what we can do, or what we can say, is we can start plugging in what I is here, just to simplify this. So we have 2/5 mr squared, but one of the r's cancel, so we're just left with r alpha. Yeah, that should make sense. Yeah, and this is also negative. Cool. And so the sphere rolls without slipping, so we know that alpha in this case, or A, is going to be equal to negative r alpha. And so then static friction here, Fs, is going to be equal to 2/5 ma. And so what we can do now here is we can plug in what Fs is, and we can solve for A here. And very quickly we can see that, so what we can do is, let's just start plugging this in. Mg sine theta minus 2/5 ma. And so then this is technically going to be an max here. And then we can say that this is all equal to max. And so then we'll solve for max. So we'll get mg still on this side, sine theta, is equal to 2/5 max plus max. M's cancel here. They're gone though. And factor out an ax here. So you get 2/5 plus 1. And so then this is going to be 5 over 5, which is going to give us a 7 over 5. And so then we multiply both sides by 5, divide by 7, and we get that ax is going to be equal to 5/7 g sine theta. Easy peasy. Okay, next up, we have a yo-yo is constructed by attaching 3 uniform solid discs along their central axes as shown. The 2 outer discs are identical with masses m, r, and moment of inertia 1/2 mr squared. The central smaller disk has a mass of m over 2 and radius of m over 2, so it's half mass, half radius. And a light flexible string of negligible mass, which is wrapped around counterclockwise around the central disk of the yo-yo. The yo-yo is then placed on a horizontal tabletop, and the string is gently pulled with constant force F. The coefficient of friction between the yo-yo and the tabletop is mu. The tension in the string is not sufficient to cause the yo-yo to leave the tabletop. So part A, develop an expression for the moment inertia, ICM, about the central axis of the yo-yo in terms of the given quantities and fundamental constants. So here, ICM is just going to be a sum of II, which is going to be equal to I1 plus I2 plus I3. And I2 and I1 are going to be the same, so then this is going to be equal to 2I1 plus I3. And so then figuring what I1 is we have that this is going to be equal to 2 times 1/2 mr squared. And then we have to add 1/2, and then we have to plug in what m is here. So this is m over 2, and then this is times r over 2 squared. So then this is going to be mr squared, and then this is going to be plus 1/2 times 1/2 is 1/4, and then 1/2 times 1/2 is 1/4. 1/4 times 1/4 is 1/16, and then we have mr squared. And so then we can add these up, and this is going to be 16 over 16 here. So this is going to be then 17 over 16 mr squared. Easy peasy. We're donezo. Determine an expression for the magnitude of the torque tau exerted by the string about the contact point with the yo-yo with the table. So remember that tau is FR sine theta or sine phi, whatever you want to use it. And in this case, theta is going to be equal to 90, so just get rid of that. And then r is going to be equal to r over 2, so then we have FR over 2. Easy peasy. Develop an expression for the moment inertia of the yo-yo about the contact point with the table. So we have to use some parallel axis theorem here. So one thing that we have to remember is that this is ICM here, and I'm just going to label that real quick. And then we'll erase the calculation that we did for ICM, but we're still going to keep it around here for this problem, for this part of the problem. Okay, so we're going to have that this is going to be I is equal to ICM plus mr squared, and where r is the perpendicular, little r is the perpendicular distance between the two axes, and so that is going to end up being, let's see, okay, so we have to do this for two different parts here. Because what we're going to end up having is we're going to have r is going to be perpendicular distance between the two axes. So what we're going to end up having here is we're going to have to say that this is 17 over 16 mr squared. That's easy peasy. And then we're going to have that this is going to be plus 2 mr squared plus m over 2 r squared. So this is going to be the distance between the center of mass of the two outer parts of the yo-yo, and this is going to be the center of mass of the inner part of the yo-yo, where the mass is m over 2. So you have to double up this part because it's m over 2. So this is technically mr squared plus mr squared, one for each of the parts of the yo-yo, plus the small part of the yo-yo. And so that's where this comes from. And so now that we have this thing over 16, we're going to have to adjust this. So we're going to have to go ahead, and this is going to be 32 over 16. And this is going to be, so we have to multiply this by 8 over 8. So this is going to be 8/16. So that's going to give us 40/16 and then 57th. 57/16 mr squared. Okay, determine the magnitude of the linear acceleration of the center of mass of the yo-yo the moment the string becomes taut. Remember that in this case here, that t is equal to I alpha, and that ACM is going to be equal to R alpha. And so then we can solve for ACM here by making a little substitution here, saying that alpha is equal to T over I. And so then ACM is going to be equal to RT over I. And so we can do a couple things here. And okay, so remember from earlier in the problem, we said that that T was going to be equal to FR over 2. And we already found what I is here. And so then we can start plugging those things in. And we have FR over 2 divided by 57 over 16 of mr squared. And so now this is no longer a function of r, because we have r, and r squared. So those cancel out. And then we're going to have to flip the 16 up to the top, multiply it, and then the 2 comes down to the bottom, and then the 57 stays on the bottom. Yeah. And then we have F over M. This is 8, so we'll put the 8 there. And there you go. And then the next couple are conceptual questions, and I'll let you guys solve those. If you guys are curious about what those answers are, come to a recitation and ask, and I'll be happy to go over those conceptual questions. A uniform beam of length L and mass MB is supported by 2 pillars of located L over 3 from either end as shown in the figure. A duct of mass MD stands on one end. The scale is placed underneath each pillar. The entire system is in equilibrium. Enter expression in terms of the defined quantities and G for the force and that the scale under the right pillar shows. Okay, so just to show you guys what this is set up as, we have these 2 pillars here, and we've got this, and I'm going to make this just a tad more accurate. And so then just imagine that my drawing is correct, right? This is L over 3, this is L over 3, which makes this L over 3, which makes this entire thing L. And that's the length there. And now they're cheating because they didn't draw this picture of the duct. It looks like it's copy and pasted. So so I can't really draw that very well, but here you go. Here's your little duck. And that's my attempt to draw a duck. He's going honk honk. So next, for the first part of the problem, we have to enter expression in terms of the defined quantities and G for the force that the scale under the right pillar shows. So we're going to have 4 different torques here. So yeah, so there's no angular acceleration or acceleration here for the duct and the beam system, so there's no angular acceleration, so that the net torque in the system about any point is going to be 0. So we can do a couple things here. We can just sum up the torques, and so from here there's going to be a couple of them. We have TD, which is going to be the duct, plus TB, which is going to be the torque on the beam, plus TL, which is the left pillar, plus TR equals 0, and this is going to be the right pillar. Okay, so and this, which each torque term represents the effect of the earth acting on the duct, earth acting on the beam, the normal force from the left pillar, the normal force from the right pillar. Okay, so yeah, this is the torque caused by the duct, by the force from the earth acting on the beam itself from basically this point here. And the normal force from the left of the pillar and the normal force from the right pillar. Okay, so this first one is going to be MD for the duct, right? Oh yeah, and it has the mass of the BE, or the mass of the beam too. And then this is going to be the force G, and then the torque is going to be how far the duct is from the beam, which is going to be L over 3, not 1/3, but L over 3. So then the beam, so this is going to be the earth acting on the beam, and so then this is just going to be mass of the beam times G, and then this center part of the beam here is going to be 1/6 from either of these pillars, so we can just write that as L over 6. And so the normal force from the left pillar here is actually going to be 0, so this term cancels out. And then we have to add on the force from the right pillar over L over 3. So we're doing the force for the scale underneath the right pillar. So then we can start to, we will solve for this force here, and this will give us our answer. So let's get this all on one side. So FRL over 3 is going to equal MBD, or MBG L over 6 minus MDG L over 3. And so now we can get rid of these 3's here, or we can get rid of the L's. The L's are all gone. And then we can multiply this quantity by 3. So this is going to give us a MBG over 2. And then this is going to be minus MD. This is a B, this is a D, G, and that's it. Yeah, very nice. And this is what they asked for. And so now what we can do is they want to enter expression in terms of defined quantities in G for the force of the scale that the left pillar shows. So now we're taking it from a different point of view, and so then this time here, this is going to be the one that goes to 0. And so this is going to be slightly different. And so now in this case, since we're using the, under the left pillar. Yeah, this makes sense, right? Unless I have my things backwards. think I got them. Yeah, we use the left pillar as the pivot point from before to find that FR is equal to that. However, we could have used the left pillar as a pivot, or we could have used the right pillar as a pivot point instead. As we and so then we can demonstrate now that we're using the right pillar as the pivot point, and we get to cancel out tau r instead. And so I'm going to leave that bottom part up there real quick. And so then we'll just get that this is m d g, and this is going to be 2l over 3, because now this is going to be 2l over 3, this distance here. Plus this b, which is going to be the same as before because it's the same distance from either beam, mbgl over 6. And then this is going to be our quantity here for fl over 3. And then this last part 0. Okay, so now we can go ahead and say that that FL is going to be equal to, we can multiply both sides by 3, and divide by L, so we can get rid of all the L's real quick. That's gonzo. So then we can say that this is MDG, just straight up. No, we have to add a 2 because there's a 2 there still. And then this one is going to be plus 1/2 MBG. And this will be your answer for L. Then what you just have to do here is you just have to now sum the scale readings. And so then we have our two quantities here, and we have to add these two equations together. Just notice that these are both 1/2 here. And this is a minus and a plus here. So then FL plus FR, this is going to sum up to 1. So this is going to be MBG plus, and this is going to also sum to 1. So this is going to be MDG. That's all you need. Okay, so next up, problem 5. To study torque experimentally, you apply a force to a beam. One end of the beam is attached to a pivot point that allows the beam to rotate freely. The pivot is taken as your origin for your coordinate system. You can apply a force V equals its components at a point R equals Rx. It's just another vector. And so enter an expression for the resulting torque in terms of the unit vectors and the components of R and F. This is doing a very long cross product that you guys should know how to do, because we did cross products in a long term, or we did them a long time ago. So go ahead and do this cross product yourself. This is something that you guys should be able to do on your own. You just gotta use your cross product formula from chapter 1. If you don't still have it, look it up. Go searching for that information. Okay, so the next part of the problem is part C of the problem, and this one will just ask you to give the angular acceleration, and so then you just have to manipulate the torque equation, and I believe that they already give you the moment of inertia. So this is a pretty straightforward question. As soon as you get the torque from part B. Okay, so problem 6. A fan has 4 blades attached to a central shaft. the blades are a certain length long, and each blade has a uniformly distributed mass of mf, which is the mass of the fan. The fan spins up from rest to an angular speed of omega f in tf seconds. Okay, so treat each fan blade as a uniform rod of length LF rotating about its end. Enter the expression for the total change in angular momentum delta L of this fan during the spin up. Okay, so we have a couple rods here spinning, or fan blades, but we're treating them as rods here. So remember, just real quick, that del F is equal to LF minus Li. And so if those fans are at rest, it has no angular momentum. So then LF is just equal to I omega F. Okay, so it's 4 blades. So, and remember that each of the moments of inertia for the blades is going to be, remember this is going to be 1/3 m. And then R in this case is going to be LF squared. This is just going to be LF. Remember this is MF. Okay, so then since there are four different blades, their total is going to be 4 times that. Okay, sorry. All right, moving on. And then we have to just go ahead and multiply that by omega f, and that will yield our answer. Give an expression for the average torque, TF, that the fan motors exerts on the fan as it spin up. Just remember that torque is in its infinitesimal form is going, or its derivative form is going to be the time derivative of L. So in algebraic terms, if you're just finding TF, this is just going to be the algebraic analog of dl, or dl dt. Okay, so if the fan spins through 7.5 rotations during spin up, calculate the work in joules that the fan motor does on the fan. Okay, rotational work is equal to the product torque and angular displacement. So we just have work is equal to tau f theta. So now you just have to determine, we just have to start plugging in our numbers here. So again, let's make this a little easier on ourselves. We have 4mf LF squared omega f all over 3tf. And then this here now is going to be 4mf LF squared omega f over 3tf, and then times theta, which is going to be 7.5 revolutions. So remember to theta, and then multiply it by 2 pi radians per revolution. And there you go. That'll give you your work in joules. And that problem is done for. Okay, next one. A point particle of mass m is equal to, well, just a mass, moves according to the positive, or the position function, which is just giving us a general position function with general coefficients, where t denotes time and x, y, t, and yeah, they're just constants, that the exponents are positive integers, and that the position function has the dimension of length. Okay. Okay, so this is just taking derivatives. Yeah, you guys can do this. Go ahead and take these derivatives in general form. Yeah, this is just more derivatives. Very nice. We have a little more cross products here. So this is practice with cross products, which you guys probably all need. So go ahead and do your cross products here. Yeah, this is just derivatives and cross products. This is just math that you guys need to know how to do on your own. So go ahead and do this problem on your own for sure. So this shouldn't be too bad. Okay. So problem 8, suppose you start an antique car by exerting a force of 250 newtons on its crank for or these are just random forces and a randomized force and a randomized time. Okay, what angular momentum is given to the engine if the handle on the crank is blank from the pivot point, some distance from the pivot point, and the force exerted to create a minimum torque the entire time? Okay, so just remember that torque is equal to dl over t in this case, and so then you have dl is equal to tau t, and then this is going to be L minus L naught. In this case, this is going to be 0, and so then L is equal to tau t t. Keep in mind here that in this case that now we have to solve for what tau is. Tau is just equal to FR sine, but sine is equal to sine of 90, so this is equal to 1. And then in this case, R is equal to D. So then we have that L is equal to F dt. And so then you can go ahead and just start plugging your stuff in there, and that should yield your answer. Okay, next up, problem 9. Ice skater is spinning her arms out and is not being acted upon by external torque. When she pulls her arms in close to her body, what happens to her angular momentum? Talked about this in the other video. If you guys don't know this, go ahead and look at the other video when we talk about this. So, yeah, another conceptual question. So go ahead and fill this out on your own. Okay, now we have the actual question. Calculate the angular momentum in units of the ice skater spinning at a certain rotation per second. So it's going to give you it in revolutions per second, and first you have to do is you have to convert it to radians per second so that we can use SI units. But then this is just going to be that angular momentum is equal to I1 omega. So this is going to be a quick and easy problem because they give you the moment of inertia in the problem, because it'd be impossible to calculate the moment of inertia of an ice skater. Okay. Okay, so now what they're going to do is they're going to have you do conservation of angular momentum. So we know how much angular momentum they had to start with at L1. And now what we're going to have to do is we're going to have to go ahead and find her new moment of inertia due to her rate of rotation decreasing. So what they're doing here is in some problems here you're going to get they're going to tell you, oh, the moment of inertia decreases to this amount once she pulls her arms in, or once she pulls her arms in, she's going to increase to this new speed of rotation or angular rotation. And so you just have to take your L1 is equal to L2, and then this is going to be I1 omega 1 equals I2 omega 2. And then you can rearrange this for I2 or omega 2 any which way you want. In this case, we're doing I2 is equal to I1 omega 1 over omega 2. Easy peasy. That's how you get it done. Okay, so again, if you wanted to find what the new angular velocity, then you would just divide by I2 instead of omega 2, and that would yield that as well. Okay, so, now in part C we say, suppose he keeps his arms in and allows the friction of the ice to slow him to this new speed. What is the magnitude of the average torque that was exerted in Newton meters if this takes a certain amount of time? So a couple things here. We just have to use our torque equation again. And on top of that, we just use that omega F is equal to omega naught plus alpha T. And so then in this case, we just solve for what alpha is. And so then alpha is omega F minus omega naught over T. And then you can plug that in. And so then you get I omega F minus omega naught over T. And so then you had the old angular we had the old angular velocity, we have the new angular velocity, and it gives you the time, and we know I from the previous problem. And so then there you have it. And that's the end of your homework assignment. Be sure to come to class and ask any questions that you need answered, and have a great day.